started looking into, it wasn't our scope of work, we just kind of started looking into the nozzle nodes, and we could see it was very above what we would expect them to be. And there was also some modeling stuff going on there that we didn't agree with. So we addressed this to the guys, and we're like, yeah, you need to do that as well. And then the real problem started, because now we needed to calculate it again and make it work. But this thing was already built and tested and everything. So it would cost hundreds of thousands of dollars, maybe millions of dollars, starting cutting this thing open, adding more flexibility, for example. So then I started playing the what if game again, changing supports, but trying to keep natural frequency as high as possible, and also that the mode shapes didn't correspond to the worst possible directions of the forces, for example. So this project wasn't supposed to be that big, but it grew to be, for us, a very big one. I think we used half a year on it in the end. Because it was so much back and forth, but the owner of the oil rig was very happy because we didn't change any piping there. We just changed the pipe support pipes, or we just removed them in some cases, because you don't need this to carry. It's carrying basically its own weight, for example. And also they had done some bad initial boundaries. So this top here was done by one company, the other top here was done by a different company. So how do you do the boundaries there? Yeah, they added some anchors at the boundary. And I was like, what's going on there? No, it's the boundary. They're going through a penetration in the wall, and on the outside of the wall is not our scope. Okay, so you've got like a velvet penetration? No. You got like an anchor support? Yeah, but how can you put an anchor? No, how should we do it, you know? Like, yeah, but then you should include some part of the other guy's scope and opposite. Especially if you're interested in natural frequency, you cannot just fix it. There is absolutely no support. So starting to kind of undoing these things generated a lot of, not problems, but it started to find a lot of things we didn't wish to find. And also another thing is that over here is a lot of green stuff that's the rigid elements. There is some supports underneath here. And I asked the guys, why do you have all these supports there? It makes it really messy because, as I said, this is 350 Fahrenheit in that area. It wants to expand in this direction and upwards, all around. And you want to restrain it just below it. And then you got quite a lot between it. And you want to really like hold it down. And then looking at each other, like, everybody does this. Yeah, I know this. I don't know why, but everybody does this below the choke and kill manifold, for example. They restrain the pipes. And in the end, I figured out, because I've been hosting these trainings in Singapore, they make a lot of these drilling units. So when I've been in Singapore, I was like, why do you add those? I'm just curious, why do you add them? What is the purpose? No, it's just how it is. Everybody has done it, and the operational temperature here is not that much higher than ambient, but the design temperature is much higher than ambient temperature. So probably it's going to be okay, but you don't know how long it's going to be okay. That's the problem. So what my personal opinion is, from talking with a lot of people adding those supports, is that it's a nice boundary to cut your calculation. It's a nice place to stop your calculation. So you stop here, and I said, okay, you can add an anchor, but if you add the anchor, you need to add at least the displacements for the manifold, because the manifold, I'll show it later, is just a big block of valves, and there's almost no piping, there's almost no flexibility. So, yeah, this is just another example of the same table as I showed before. So in the end, the problem was that we needed to do vibration analysis of each and all of the piping line numbers that you see here. That got too much to handle in one model, so we started separating them out into smaller models. So to calculate the fatigue stresses in each and all of the pipes, just to clear them out, because we changed the boundary conditions of them. We didn't know if they were going to shake afterwards. As I mentioned, it's a bit hard to see, but you can see all the green stuff is the rigids. There's a pipe, and the same on the other side. So basically, just a bunch of rigid elements bundled together. So the flexibility needs to be on the piping side. It cannot be on the electric side. But a lot of companies keep on fixing them just below here. And you can see it's quite long. It will expand. It gives major problems. So we've done a lot of these calculations for National Oil Barco back in Norway. And typically we end up with very low allowable loads, because then you do the equipment alone, you don't have any control of the piping around it. So we assume that all nozzle loads, for example, are sustainable. So that gives you a low allowable stress compared to if it's thermal loads that you're dealing with. And also we are working with API flanges on these ones. So you got the API TR, technical report, 6AF2, which is basically a lot of FEAs done of the API flanges. It gives you the allowable bending moments of the flange depending on your axial tension force and your internal pressure. And those calculations down there are conservative, since they don't take into account how the gasket is acting, for example. They're just adding fixed supports here, and they see when they don't have any tension, when they don't have any compression on that point anymore. It is failing, it's opening up, and the liquid inside is going outside. The liquid inside is going outside. So we did much more detailed analysis with nonlinear material models, the gaskets, and we found a lot of these flanges to be much stronger with regards to the leakage criteria compared to what the API technical report says. And also the technical report says that you can use your own sound engineering judgment to calculate it. Yeah, just very shortly about the burst discs. So this was burst disc for liquid. It was the mud, and they were supposed to burst at 10,000 psi. And I haven't really found much good literature on burst disc used in liquid systems. I found a lot of them with regards to gas, because you got the expansion of the gas and the burst disc burst. So when you have all of these, it's not that much of piping, so the pressure drops fairly instantly. And I did some hand calculations by myself, and I like calculating between 2 to 10 milliseconds, depending on a little bit of how we approach it. It will drop from the design pressure down to 0 because it was atmospheric tanks on the other side of the burst disc. And I found some very old reports and technical documents that if I use the same numbers that I've been using in the experiments, it was quite similar to what I would find in my equations. So we did that because if you take the cross-section area of your pipe, multiplied with the pressure you got on one side, you get an insanely big force acting on this thing. But it goes like this, I cannot even do it quick enough, you know. And the third thing is that they tested this because they almost had no supports around it. And I asked the operators, what happened when you tried to burst the discs? He said, bang, nothing happens. So we did some time history analysis of this just to see how it affects on the piping. And it was, if you were conservative, the longer the time duration is, the more of the load will be applied to the piping. So, or it gets time to react to the load, basically. So So we're doing some conservative approaches, and still we found stresses like 50, 60 megapascal with the SI Russian stats, 69, 10. KSI.
No, look at
I'm
it.
really bad, I'm sorry. No, it's like 10 KSI, 690 bar. It's like 1 KSI. Yeah, 1000 PSI. So, that kind of brings us to the end. The lessons learned from this project, it was like, you need flexibility and you need to keep your natural frequency up. So, try to figure out how to do that. For us, that was quite a big lesson learned because we had to tweak the system. We could, well, probably if there was no other solution, we had to do something with piping here. But as I said, it was already, everything was completed there. So they just wanted to ship this thing off and getting it within the allowable loads on equipment, because the stresses in the system wasn't a problem. The stresses was fairly low because the nozzle loads, the allowable nozzle loads were so low, so you could almost like apply no force to them. So the forces inside of the system wasn't that bad. Yeah, and including this structural stiffness, that totally changed the natural frequencies. And even before this project, we've been doing that as well. And then don't add any fictional anchors. I've seen them in analysis several times. We're fighting with people over them. I don't like them, unless you have a really good reason that nobody told me yet. Yeah, and also confirming the boundaries of what has been made is super important. Like on FPS, so that's here in Mexican Gulf, we did the analysis of it. That was before I started up Stressman, and we got a phone call from the operator saying a 20-inch pipe is moving almost 1 foot. Are you sure? Do you have your units correct? 1 foot, 1 inch? Not 1 foot. And they were like, no, 1 foot. Cannot be. So we checked the analysis, and we got like a displacement that was 100 of that. And we called them back up. So this is something to do with the pipe supports probably, because it cannot move. Then the pipe support should be moving along with it. So everything in place. Every single pipe support on the pipe rack, rest support. So when the slug forces were going through the system, it was really high force. It was just pushing it. So confirming boundaries is really important. And I don't remember who said that, but you talked about the daily life of the engineer. At least this is my daily life. I eat, I sleep, I stress. And I repeat it the next day. All right?
Very good, man.
Thank you.